Hey, before I get started on this talk, I just want to make, at the end of the last talk, there was a discussion about phosphorus in rainfall water, and I really want to emphasize, phosphorus has no gaseous phase, okay? So the amount of phosphorus that's going to come down in rainfall is going to be nearly zero. And if you do get any in rainfall, it's going to be through particulate. Any particulate matter that might be floating around as it comes down in rainfall, any phosphorus that's on it might come down. So, all right. But here we're talking about phosphorus structures, and the target, we're going to be focusing on dissolved phosphorus, all right? Not particulate phosphorus, not phosphorus that's bound onto soil particles. We're getting after dissolved phosphorus. Particularly phosphorus structures are targeted to the source of dissolved P from legacy P soils, not recently applied manure, not recently applied fertilizer. We have very good best management practices for that. This is getting after legacy phosphorus soils. More about that in a second. When I say a legacy phosphorus soil, I'm roughly, approximately talking about soils that are around at least 100 milligrams per kilogram of malate 3 phosphorus. Okay, dissolved phosphorus, why are we focusing on dissolved phosphorus for this? Quite frankly, dissolved phosphorus is a more potent eutrophication agent than particulate P. There's been a lot of research the past several years have shown that. The re-eutrophication of Lake Erie is attributed to dissolved phosphorus. And the reason why is because aquatic organisms can immediately uptake dissolved phosphorus from water. With particulate phosphorus, that's not necessarily true. You have phosphorus bound to a soil particle, it gets deposited into a reservoir or stream lake. It may or may not become bioavailable. It may adsorb dissolved phosphorus from the column. It just depends on that particle, the mineralogy, depends on the conditions. Dissolved P is a major target, and the issue with it is that it's very difficult to control once your soils get built up very high in phosphorus. We've got a lot of great best management practices for reducing particulate phosphorus. Quite frankly, anything that reduces erosion will reduce the transport of particulate phosphorus. But even if you have a legacy P soil, if you control 100% of the erosion, you will still leak out dissolved phosphorus every rainfall event that you get. Yes, sir? Yeah. Oh gosh, you can ask me to do that in public. It's about half as much. Pounds per acre is half as much as milligrams per kilogram. Milligrams per kilogram is parts per million. So it's half, yes. Thank you. So in this, what we have here, here, this gives you a benchmark. Your target agronomic optimum in tri-state area is around between 20 and 30 milligrams per kilogram of malate 3P. So once you get up around 100, you have a problem when it comes to water quality, at least. That's approximate. It can be a little higher, a little lower, depending. But the big problem with the legacy P is that it stays elevated for so long. All right. Here's a study from Maryland where they artificially built up soil test P levels several different degrees, all the way up to 600 milligrams per kilogram. Their agronomic optimum level is about 50 milligrams per kilogram, so they way overshot it. And then they stopped applying phosphorus, put in corn, wheat, beans rotation, and they measured drawdown. They wanted to see how long it would take to draw that phosphorus out of the soil and draw the malate 3P levels down. You can see it takes a long time, and they're still not even close to the agronomic optimum level. And what they concluded from that study was that, and other studies have come to similar conclusions, is that if your soils are built up to around 300 milligrams per kilogram malate 3 phosphorus, it's going to take 20 to 30 years after you stop applying phosphorus for them to come back down to that agronomic optimum level of around 20. Well, in this case, around 50. In tri-state area, we're shooting for more 20 to 30 milligrams per kilogram. So the problem is that while we do that, during that process of drawdown, we're not applying phosphorus, we're drawing that soil down through the crop, getting it off the field, getting it out of the watershed. It takes decades. And during that time, every time you get a flow event, like Brittany had showed, every time you get flow events, water starts moving through that system, you're going to carry off a load of dissolved phosphorus. It's going to dissolve in it every single time for decades. It's a long-term problem. So this is the impetus for why phosphorus removal structures were developed. Essentially, in theory, they're very, very simple. It's nothing but a giant landscape scale filter. All right, you have a media that has a high affinity for phosphorus. You force water to flow through it. The phosphorus binds to that media through a variety of different mechanisms, depending on what you got, and clean water goes out. It's like a giant Brita filter. That material becomes saturated with phosphorus eventually. You clean it out and replace that media. So the filters, the pea removal structures can look a lot of different ways. They'll be very diverse in appearance, but they all have to have three main components. All right? The first one's pretty obvious. You have to have a pea sorption material, your filter material, I call it a PSM. You have to have a PSM in sufficient quantity. You have to have enough of that filter material to be able to treat an appreciable percentage of the load for your site. All right. Second thing is you have to force water through that filter media at a sufficient flow rate and contact time. Right. The water has to flow through it. If you can't force the water through it, if the water bypasses it or just goes over the top of it, you're not really treating. You're not treating the water. You're not removing it. So it's very important to design these to be able to handle a appreciable flow rate for your site. So like I said, in theory, these work. They're very simple the way they work. Designing them, on the other hand, is a bit more involved. They are engineered units. They also need to be designed with the ability to replace the materials routinely after they become saturated. So with those three components, you get a whole diversity in appearance of these things. But as long as they have three components, you've got a pea removal structure. I'm going to show you some examples of those here soon. Talk briefly about the materials that we use, the filter media, the PSMs. A great majority of them can be industrial byproducts, various byproducts. Some of them are byproducts of mining. Some of them are naturally occurring media. They come from various industries, steel slag, metal filings, drinking water treatment residuals, flue gas gypsum, fly ash, all kinds. And they vary in their ability to remove phosphorus. Some are more efficient than others. When you're using industrial byproducts, they also need to be tested for safety because not all of the materials, just because they can remove phosphorus doesn't necessarily mean that they're safe, so they need to be screened for safety. There are also manufactured pea sorption PSMs, and the manufactured media, so there's a couple of them made in Ohio actually. They tend to be very efficient. They're usually either iron or aluminum oxides. Generally, PSMs are either going to be rich in aluminum, iron, or calcium. And it is your iron and aluminum oxides that tend to be the most efficient. So your manufactured ones are usually either aluminum or iron or some mixture of both. They're very efficient on a per mass basis, but they're also extremely expensive. Most of them are cost prohibitive, not even worth using them, quite frankly. I'll give you some examples. This one's in Ohio, Fe Ozorb made by Biomax. ABS, it's called Biomax, made by ABS Materials. Imbrium, Actigard. There's another one. There's one in Ohio called Metamateria, Iron Sponge. Most of them are cost prohibitive. Some of them are less expensive, and they might be doable. We're testing some of those in the field with regard to economics. So the heart of the pea removal structure is the ability of that filter media to remove dissolved phosphorus with continued loading. So to design it requires some quantification of the ability of that media to remove phosphorus with loading. So at the heart of it, we have to design what I call it a design curve. And it's simply a mathematical description of how much phosphorus is removed as a function of loading to that media. All right, that's the heart of it. You need this quantification to be able to determine how much of your particular PSM you need to meet the target for your site. So this design curve, and it's determined under a flowing conditions. It can't just be in a test tube in the lab. It has to be determined under a flow-through test. It's going to be different for different filter materials. That should be fairly obvious. But here's the kicker. It also varies depending on the inflow concentration and the retention time. So to aid in the design of the structures, we developed software. It's called P-Trap, Phosphorus Transport Reduction App. It's completed. It will be freely available through the USDA. Right now, it does what it's supposed to do. We're working on the cosmetics right now and trying to make it a little more user-friendly. But essentially, it is engineering for dummies. We're trying to allow the non-engineer to be able to design these structures. So there's several inputs, any software models you'd expect. You need to know something about your site. You need to know something about the site hydrology. The user has to know something about what peak flow rate they want to be able to handle. You want to be able to handle 300 gallons per minute, 500, 50, what do you want? You need to know something about your annual flow volume. How much phosphorus, how much water do you want to be able to treat per year? Ideally, you want to be able to design it to be able to handle 100% of the flow volume. And obviously, you need to know something about what's the dissolved P level in your water, right? So the dissolved P level combined with the annual flow volume gives you your phosphorus load. As a user, you have to make a decision on what size area you're willing to sacrifice to build these things. As a user, you have to choose a target. So don't ask me, and this is over, don't ask me, how much P will they remove and how long will they last? Okay, you choose that as a user. It's an engineered unit. So you choose what percentage phosphorus you want to remove over a given lifetime. So I always design mine for 40%. That seems to be the magic number around here, right? 40% cumulative removal over a given lifetime. Say 40% of the cumulative load of all the phosphorus that flows from that site over the next 5 years or the next 10 years or 20 years. Whatever you choose as a user. Quite frankly, I build them as large as I possibly can. That's feasibly and economically possible. You need to know something about the characteristics of your PSM. You need to have that design curve and know about its ability to remove phosphorus. It needs to be screened for safety, and you need to know something about the physical properties because you are channeling water through it. So things like bulk density, porosity, hydraulic connectivity are critical. So you throw all this into it, plug it in, and it spits out for you a prescription for a design for your site to meet your goal with your media. The most important thing it'll tell you is the mass of PSM that you need and how to orient it in order to meet your flow rate goals. I'm going to give you some examples here of different structures. But before I do that, I want to say this. I wish I could stand up here and tell you that we could just build these nice little cartridges or stick these little tiny filters into ditches or the end of tile drains and we just solve the problem. But if it were that easy, we wouldn't have a problem. All right, so we're not talking about pounds of filter material. We're talking tons of filter media is what it takes to remove an appreciable load. So if a site is worth treating, it is going to require a large mass of PSMs. Like I said, I wish this worked. I wish we could just stick out these little cartridges in these small modular boxes and that they be remove an appreciable load, but they don't. Sounds great, portable, easy to install. Problem is, it only works in limited situations. For the obvious reason, it has a very small mass of filter media in it. So you have to ask yourself, with what it's removing then, is it even really worth doing it? So you got to go big or go home. They also have a poor flow rate. And again, if you can't treat the water, if the water doesn't go through it, you're not treating it. Filter socks is another pipe dream that I wish were true, but it's not. Filter sock filled with a PSM. Again, it suffers from the same problem. You can't fit hardly any filter media in that. You've got a limited mass, you've got poor contact, and you've got poor contact time. All right? These don't work. So currently, I'll say that the technology is effective, but it can be improved. We've built a lot of structures throughout the world. We're continuing to build more. We're on the verge of becoming more and more efficient and economic. That's where my research is right now with regard to P removal structures, is making it more economical and more efficient, particularly in tile drain situations. It is included through the NRCS Standard number 782. I will say this. It is interesting. You look at the Ohio H2O list of practices, right? I'm going to back up, talk a little about just dissolved P in general. You look at those list of practices, and we see a lot of things that are great for particulate P, but many of them are not going to do squat for dissolved P. Your two-stage ditches, buffer strips, cover crops, all these things. They do nothing for dissolved phosphorus, all right? But I don't know who made that decision, but yet we don't see dissolved phosphorus removal structures on that list. I don't know. They didn't ask me. All right, so I'm going to give you some examples here of structures that either I built or had a hand in or designing, just to give you a feel for what they look like and what they can do. This is one. Keep in mind that some of these are old, and we're getting much, much better at making them more efficient and cost effective. This was on a poultry farm in eastern Oklahoma. It intercepted runoff water from around the barns. It removed 7.5 pounds of dissolved P in 2.5 years, 23% of the 2.5-year load. We had 40 tons of an aluminum-treated slag. It handled about 1,000 gallons per minute. Cost about $5,000. This is a smaller one. Same thing. It captures surface water. This is on a golf course, also in Oklahoma. It contained only 3 tons of a sieve slag, 1/4 inch minus. I'm going to mix units here for you. So, only 3 tons, normal slag, not treated with aluminum or anything like that. Over 8 months, it removed 25% of the load. Then we cleaned it out and replaced it with a slag material that was smaller in particle size, 0.5 millimeter minus, sorry for the metric. And it removed 33% of the 16-month load. These cost, building the structure initially cost about $2,500, and then replacing it, refilling it hardly cost anything at all. Once they're built, you just replace the media. Ditch filters, this is something we built a lot of on the eastern shore of Maryland, treating surface water. These are nice because the ditch acts like the box to retain the material, the PSM filter material, all by itself. So it allows you to use a very large mass of PSM. See here, you've got you start out with a bed of drainage pipe, and then you backfill it with your PSM. You can use a flow control structure to maintain a head of water on top of it. So once it's built, there we go. After it's built, you see the water flows down that ditch, gathers on top of the PSM, flows down through it into that drainage pipe at the bottom, takes it around to another ditch. Very easy to build and fairly low cost, less than $4,000. Works great for ditches. Surface water works good for some of the materials we were using on that worked okay for surface water. We monitored several of these. We used a fairly mediocre PSM. We used a highly sieved slag material. This is work we did with Josh McGrath when he was still at University of Maryland. Highly sieved slag and also FGD gypsum. They're not that great, so we ended up with about 25% cumulative removal over 2 years. Was about typical performance for these. We can use better materials and do a lot better than that. Here's a greenhouse filter in research greenhouse at Purdue. We collect all the water that drains from the pots. It's got about 20 milligrams per liter of phosphorus in it. That's way higher than anything expected in ag. We use 190 pounds of mine drainage residuals to treat it, iron oxides. It's still removing over 90% of the phosphorus after 2 years. Costs about $500. Bioretention cells. This is an urban best management practice, kind of a temporary storage of storm flow water and then filtered through the soil. You replace that soil with a PSM, it becomes a P removal structure. So we built several of these in eastern Oklahoma. 147 tons of a sand fly ash mixture, 95% sand, 5% fly ash. They work quite well. Don't ask me how much they cost. I didn't have the budget for that one. So let's shift over more towards tile drains, getting at subsurface water. This is a slag filter we built in Indiana. We combined it with a blind inlet, so we were capturing some surface water and then channeling it into the P removal structure. But dominantly, by far, over 90% of the flow was coming from the tile, was subsurface water. And we had a distribution manifold, push that water down to the bottom of the bed of slag. This is a normal slag, not treated with aluminum. Water flows from the bottom upward, and then discharged out. It was about 36 tons of slag. Tremendous removal. 55% of the load over 1.5 years for 43 pounds of dissolved phosphorus removal. That's great. That's the good news. Bad news is it didn't do much after 6 months. Okay, cost about $11,000. We learned something very valuable from this. From this and another study that we did with Kevin and Kevin King and his postdoc Vinayak, several of his postdocs actually. We learned this. You cannot use regular slag for treating tile drainage water. You can use it for surface water. Tile drainage water kills slag. And the short answer, the short explanation why is because the bicarbonate in the tile drainage water competes with the phosphorus. It uses up all the calcium in the slag. So bicarbonate kills slag. Can't use it for tile drainage water. Great for surface water. Here's another tile drain. Doesn't look like a tile drain. This is a tile drain that outlets into a ditch. And we used, in this case, an aluminum-treated slag. So it was different. This worked a little better. We had 50 tons of aluminum-coated slag, removed 30% of the cumulative load over 14 months for 6 pounds. It was poorly constructed. It wasn't constructed the way that it was designed. Cost about $15,000. Here's another tile drain structure. This one we did with Larry Brown, also with Kevin. It's got 30 tons of an aluminum-treated slag. This is buried underground. And after 2 years, I think it was 2 years. Yeah, after 2 years, it's still removing 40 to 95% of dissolved P per event. And we're working on gathering more current data to include loads. It costs about $13,000. So again, it's an aluminum-treated slag. It works okay for tile drain water, but not regular slag. Blind inlets. Blind inlets traditionally use limestone as their medium, and they're designed mainly to remove particulate phosphorus and sediment in general, and they're good at that. This is one we had monitored for around 10 years. It removes almost zero dissolved P. Okay? Limestone does not remove dissolved P hardly at all. Good news is blind inlets are cheap, $2,000 or less. Negligible dissolved phosphorus removal. It removes some herbicides. However, if you replace that limestone, the blind inlet, with a PSM, which we did in 2016, we used slag instead of limestone. And what we found was that in 2018, we removed 46% of the annual load for that year just by changing over to a sieved slag. And again, slag is low cost, and building blind inlets is low cost. Slag, the regular slag worked okay on this. Why? Because it's surface water. It's not tile drainage water. This is an example of a regeneratable tile drain filter. Something we want to do to make it much more economical is to use materials that we can regenerate so we don't have to clean them out. Instead, regenerate them in situ and just keep on trucking, keep going. This one we built with Margaret Kalsick, Larry Brown, Kevin King. We used a manufactured PSM. We got one of those expensive, high-pollutant P-sorption materials. It was pretty expensive. But we thought, well, it's efficient per unit mass, and if we can recharge it, it might be worth it, actually. So we got 2.5 tons in this tank. It flows from the top down. It's designed to remove 40% of the 10-year load. And then after 10 years, we plumbed it so that we can come back in and regenerate it, strip that phosphorus off, and keep going without having to spend the money on new media. Cost about $12,000 to build that. Briefly on stripping phosphorus, this works for mostly, especially for iron oxide-rich materials, sometimes aluminum, depending on the mineralogy. But essentially, you strip it off with a hydroxide solution. So we've done this in the laboratory. It kind of guided us in designing this field unit. But you strip it off with a potassium hydroxide. And what we found in the laboratory is that depending on the concentration of potassium hydroxide to be used and the number of recirculations, we can get a pretty good recovery of that phosphorus. It's not enough to use as fertilizer, so before you ask that question, I'll tell you that right now. It's just a smidgen compared to what you're actually losing. This material I have great hope in. It's a byproduct. It's very cheap. They're metal shavings. It normally goes back into the steel industry to be reused to make more metal. We mix this with sand or gravel at 8%. I don't recommend using more than 8% of the metal shavings, but the metal rusts, and the rust form is iron oxide, which is a high affinity for phosphorus, and these things are highly efficient per unit mass. This is our pilot scale box. We haven't built one in the field yet. It's got 200 pounds of the metal sand mixture on the left and the metal gravel mixture on the right. We put 100,000 gallons of water through that little box, and it removes 77% of that cumulative dissolved phosphorus load. And that metal is cheap. It's $200 a ton. You don't need very much of it because it's efficient. If we can make this work in the field, this I think this will be the most cost-effective thing. We have plans to build several in the field this spring and summer. Briefly on economics, it's very hard to put a measuring stick on it of I can tell you how much these things cost, but is it worth it? And the only measuring stick I have, the best measuring stick we have, is the cost of phosphorus removal at wastewater treatment plants. All right, so a wastewater treatment plant costs them between $50 to $800 to remove a single pound of phosphorus, and that's total phosphorus, not dissolved. Keep in mind, it's harder to remove dissolved phosphorus, and in wastewater treatment, it's a lot easier. You get a higher concentration, and it's a nice point source. With non-point, it's dilute, and it's coming in from many acres. So it makes it worth more to be able to remove dissolved phosphorus compared to than wastewater. But some things we can do to make it more economical. We could cut the cost in half if we regenerate the media. If we can regenerate media in situ, it'll nearly cut the cost in half. Also, I mentioned this the last slide, metal shavings show tremendous promise as a economical PSM. So, some conclusions here and talk about the future. Use normal slag, that's your electric arc furnace slag, your blast furnace slag, not treated with aluminum, for surface water only. Blind inlets, things like that. Do not use it for tile drain. The alkalinity, or the bicarbonate specifically, will kill that slag. It'll be short-lived. It'll work great for 6 months, and then it's dead. Aluminum-treated slag, on the other hand, seems to have much greater longevity for tile drainage water. We have other slag and other materials to be evaluated that have some decent promise. Some of the less expensive manufactured media also show some promise as well. We're going to build some structures built out of those with Kevin and Jay Martin and his crew here over the summer. And there's other PSMs to be evaluated. People send me PSMs from all over the country all the time. I got a long list of them I need to keep evaluating. So the current research is in regeneration, in situ. Also, building them to flow from the bottom up. If we can do that, it gives us a lot more flexibility in reducing the footprint of these things. And we've done it for slag, but can we do it for iron-rich media? And that's a little bit more challenging because then you've got potential reducing conditions and solubility of that iron. So that's something we need to work on. We are working on right now. I got a PhD student working on it now. Also, we need to build some structures using metal shavings in the field. We need to start training contractors how to build these things. So to that end, I'm working with the NRCS, ASA, and ASA-BE and putting together these training modules so that people can get certified in how to design a peer removal structure. And that, combined with the software, being training in how to use the software, the hope is to get it out there so people can actually design them and start building them. It's a book, lots more details, needs updated already, but is what it is. There's a ton of people I'm going to forget to mention, but this is a whole body of research, okay? And I can't do it by myself, so there's several people and groups that have been key on this. Kevin King's group, Larry Brown, Margaret Kalsick, Nathan Stolzfus and his crew, Jay Martin, TNC, particularly Jessica and Stephanie Singer. Justin McBride's been a great help. Aaron Heilers, Josh McGrath. I'm sure there's others here I forgot, but it is a whole body of work, and we can't do it alone. So, any questions? Yes, sir.
What are you currently doing with spent material?
Spent material, it depends on what the material is. Most of the structures we've built so far have been steel slag. And the number one use of steel slag currently is in construction, especially roads. Many state DOTs use slag to build roads. So what we found is that the farmers, it's a great construction material. It's gravel. I don't know if you've ever seen it, but it's basically gravel. And so the farmers like to use it to put on their farm roads, on their dirt roads. And quite frankly, who couldn't use an extra pile of gravel? Yes, sir.
What
happens if your media goes anoxic, the redox still?
Okay, so that is an issue for the iron.
Can you repeat the question?
Yeah, okay, sorry. The question is, what happens if the media goes anoxic? Okay, that is an issue for the iron oxide-rich media. And that is why I've never built a field structure with iron oxide-rich media that flows from the bottom up. From the top down, it's free draining in between events. You've got oxygen. But if we build it to flow from the bottom up, then in between all events, it's going to be saturated in water. It can possibly go anaerobic. And if it goes anaerobic, it's iron oxide-rich media, it'll start to dissolve a little bit and could release some of that phosphorus with it. So we're doing research on that right now. But that's exactly why I've not built an iron oxide structure from the bottom up. So far, I'm keeping those top down. I'm hoping to be able to do it from the bottom up. Yes, sir.
How do you keep the material from sedimenting in? How do you keep fine particulates out?
So, okay, question is, how do we keep fine particulates from clogging these things up? And the answer is, you should use other best management practices to prevent particulates soil from getting there in the first place, right? We've got much better best management practices for reducing sediment and particulate losses. It will filter out particulate P, but it's kind of an expensive way to do it. So, the short answer is you should only be doing this on sites where you've got erosion under control already, and the soils are built up very high in legacy P. So you just got to keep sediment out of it through other means. It'll remove it, but at what cost?